Hello students, I am Saili Rathod from International Center of Excellence in Engineering and Management. Today I am going to present a video lecture of Digital Electronics, subject code CSE 204. In today's video, that is in video number 13, I am going to cover the topics that is logic families, TTL, ECL, MOS, CMOS families. These topics are from the second unit, which is Introduction to Analog and Digital Signals. So students, in this unit we have seen up till now Introduction to Analog and Digital Signals, that we have seen the characteristics of analog and digital signals, their representations. After that we have seen different types of gates. We have seen the classification of gates. Then we have seen each gate in detail, that is basic gates and or NOT gate. Then we have seen the universal gates. After that we have started with the logic families. Then in the previous lecture we have studied the features of these logic families, and then we have finished the topic, that is RTL and DTL. So two logic families we have studied up till now. In today's video lecture we will cover the TTL, ECL, MOS and CMOS families. So let's start with today's video. These are the topics which we have seen in previous lecture. We have seen what are the different logic families, that is RTL, DTL, TTL, ECL, CMOS. Then we have seen features of logic families. First we have seen fan in, then fan out, then power dissipation, noise immunity and propagation delay. All these points we have seen in detail in previous lecture. Now we will move ahead as we have covered the RTL and DTL. These two logic families we have seen. We have seen the circuit diagram, then we have seen the truth table for which these circuits are used to design. Then we will see now the TTL. Okay, so let's start. TTL, that is transistor logic family. So this logic family is named because it is the combination of transistors. We have used transistors for designing the circuit. TTL family is a modification to the DTL. It has come to existence so as to overcome the speed limitations of DTL family. The basic gate of this family is TTL NAND gate. Okay, so as we have seen the previous, that is DTL, diode transistor logic, it was used to design the NAND gate. So for 3-input NAND gate we have seen the circuit diagram. Now the TTL is also the modification, or we can say it is similar to DTL, but it is invented only for the speed, as the DTL was having some speed limitations. So for that improvement we have introduced the TTL. The modifications to DTL NAND. The diodes D1, D2, D3 are replaced by emitter junction of a multiple emitter transistor labeled T1. Now see the circuit diagram. If you compare this circuit diagram with the DTL circuit diagram, then you will realize that here there is change in this part. Okay, so here 3 diodes were used, D1, D2, D3. Now these 3 diodes are replaced by the emitter junction. Okay, and here 2 diodes were there which are replaced by the 2 transistors T2 and T3. So if you compare DTL and TTL, then there is a replacement of this part and this part. Other circuit diagram is similar, the symbol is also similar, and the truth table is also same. That is for 3-input NAND gate. So first point says that the diode D1, D2, D3 are replaced by emitter based junctions of multiple emitter transistor. Okay, now this transistor is called T1, is called as the multiple emitter transistor. As you know what is transistor, it is having a collector, a base and emitter. So base collector emitter, but here the emitters are multiple. 3 emitters are shown in the diagram, so it is called as the multiple emitter transistor, which is labeled 1 T1. Now the diode DA is replaced by collector base junction of T1. There was a DA here in the DTL circuit. Now this DA is replaced by T2, and the diode DB is replaced by emitter base junction of transistor labeled T2. So the D2 is replaced, DB is replaced by the T2 transistor T2. So I think the concept is clear to everyone, that how we can design the TTL and how you can compare the DTL and TTL. So let's move ahead. The working of this circuit. Now we will see the working of the TTL. There are 3 cases. First case is when at least one input is low, transistor T2 and T3 are in cut off. Okay, now means what? If there are 3 inputs, input 1, 2 and 3. If all the 3 inputs are 1, then what will happen? This transistor will be in saturation region. It means this transistor will be on. If T1 is on, then obviously the T2 will also get in saturation region, and this will also get switch on. It means if this is on, this is on and this is on, then the current will flow like this and it will go to the ground side. Okay, so means if all the inputs are 1, then the current will go to the ground. And if the current flows towards the ground, then obviously the current will not flow towards the output, and thus the output will be 0. Okay, so this condition, you have to remember. Here you can see the last case of the truth table. All the inputs ABC are 1. Then the final output, that is A dot B dot bar, B dot C bar is 0. It means if all the 3 inputs are 1, then the output is 0. And for the rest of the conditions, if any of the input is 1, if any of the input is 0 or all the inputs are 0, then in that case this transistor, if any of the input or all the inputs are 0, then this transistor will not get on. This transistor will also not get on. This will also be not switched on. Then what will happen? The current will come and go towards this direction, and thus as the current passes towards the output will be 1. So these are the rest of the conditions. Okay, so first case we have seen this. If all the inputs are 1, then the output will be 0. If any one of the input, it means when all inputs are high, T1 operates in active inverse mode, driving T2 and T3 in saturation. Since T3 is on, the output is low. Okay, so the conditions are not in sequence, but you can explain this from this truth table. Then the case 3, while all inputs are high, if any of the inputs suddenly goes low, then T2 and T3 will be turned off when stored base charge is removed. The collector base junction of T1 is back biased and T1 operates in normal active region. A large collector current T1 is in such direction that it helps removing base charge of T2 and T3. In this way, the circuit speed is increased in TTL over the speed of DTL. So this case 3 completely explains that how the speed is increased by using TTL as compared to the DTL. Okay, so if you are asked a question on TTL, then you should remember this circuit diagram. This is very important. Then you have to draw this truth table and you have to explain each and every case, how the output changes according to the input. Okay, so this is all about the TTL. Now the next family is the ECL, that is emitter coupled logic. ECL logic family implements the gates in differential amplifier configuration in which transistors are never driven in the saturation region, thereby improving the speed of circuit to a great extent. Here, as we know, the fastest working family is the ECL. We have seen this in the first lecture. First means the first lecture of the logic families. So the ECL family is fastest of all logic families. This point is very important. ECL is the fastest of all logic families. And which was the least power consumption family? It was the CMOS. CMOS is the family which consumes least power. The basic gate of ECL family is NOR gate. OR and NOR together, means you can use this for OR as well as for NOR, as shown in the diagram. The output 1 is OR output, while the output 2 is NOR output. So here in this diagram you can see there are two outputs. This is output 1 and this is output 2. This is output 2. So output 1 is for the OR operation and this is for the NOR operation. And as we have explained that it is a differential amplifier. So T1 and T2, they are connected by using the common emitters. We are saying this family as the emitter coupled, means what? Both the emitters of T1 and T2 are coupled together. So it is called as the emitter coupled, or we can say the differential amplifier configuration. So the second point, basic gate of ECL is NOR gate. The output 1 is for OR gate and output 2 is NOR output. Now the transistor T1 is applied with input and additional inputs are applied to transistors T1 bar, T2 double bar and so on. In this figure you can see there are multiple inputs, input 1, input 2, input 3. So here T1 is connected in parallel with the other transistors T1, T2, T1 dash and T2 double dash, like this. After that the VCC here this is positive side and this is negative side. Now the third point says that T1 and T2 are connected in differential amplifier configuration. Differential amplifier means what? Here you can see the both emitters differential amplifier configuration and both the emitters are coupled together and T1 is connected in parallel with the other transistors. These are the outputs, two outputs, these are the three inputs. This is for NOR gate and this is for OR gate. Now we will see how does the ECL works. Transistor T3 and T4 are emitter followers used for DC level shifting of output voltages. T3 and T4 means these two transistors T3 and T4 are the emitter followers used for DC level shifting. After that the positive supply terminal of the circuit is grounded while negative supply terminal is at negative 5.2. So this is negative 5.2. This is done to minimize the effect of noise introduced by the power supply. So why this positive and negative concept is applied? Just because we have to minimize the effect of noise introduced by the power supply and also to protect the gate from short circuit that might occur accidentally. Both the outputs high, low or and NOR are negative. Thus, to interface this logic family with other, a transistor circuit is needed which converts negative voltage to compatible positive voltage levels. So this circuit diagram is explained here completely. If you are asked about this circuit diagram, you need not to write every value of the resistance. You can just write down T1, T2, T3 or R1, R2, R3. This is just an example. So here some particular values are assigned in the circuit diagram, but if you are asked in the exam, you can write just the symbols or the representation of the components. Now this we have seen the ECL. After that, next logic family is the CMOS. So before going towards the CMOS, we will see the metal oxide semiconductor family, that is MOS. So MOS logic family implements the logic gates using MOSFET devices. MOSFETs are high density device which can easily and economically fabricated on ICs. So these logic families are very easily fabricated on ICs. So you can replace the whole circuit diagram by the IC. MOS logic gates can be fabricated using either only NMOS or only PMOS devices. MOS logic is vastly used in LSI, that is large scale integration, and VLSI devices, that is very large scale integrated devices, such as microprocessor chip due to their high density characteristics. NMOS NOR gate is shown in the figure. Now in the next slide you can see we can use the MOS logic family for NOR as well as for NAND. Okay, so here we have shown the circuit diagram of the NOR, then we have shown the symbol of NOR gate and the truth table. Here the circuit which we can use, the MOS circuit, metal oxide semiconductor device circuit for NAND gate, the symbol for NAND gate and the truth table. So now we will see one by one the operation, but before that we will see these last 2 points which are very important. If both transistors T1 and T2 are off, this is for the NOR gate. Okay, NMOS NOR gate, and so both these conditions are for the NOR gate. If both transistors T1 and T2 are off, that is A equals to B equals to low, then the output is high is equals to VDD. Means VDD will be high. So we are seeing the NOR gate. So now you can see in the circuit diagram, if both the inputs are low, if you give inputs both 0, here 0 and here 0, then this transistor will be switched off, this will be also switched off. So the current which is passing from VDD, it will come up to this point, and if the transistors are switched off, then there is no path for conduction, so the current will go in this way and it will give here 1. Okay, so this is the first condition. Now the second condition, if A equals to 0 and B equals to 1, it means this transistor will be in cutoff region and this will be in saturation region. Now the current will come like this and it will flow from T2 and it will go towards the ground, and thus the current will pass towards the ground, thus there will be no current at the output side. So we will get the output as 0. Similarly, the third condition, if the input A is 1 and the input B is 0, it means this is in cutoff region, this will be in saturation region, so current will come and pass like this and thus the output will be 0. So this is the third condition. And the last one, that is if both the inputs are high, if it is high, then this will be in saturation region and this also will be in saturation region, thus the current will come and go towards this direction, current will pass through T2 and will get grounded, so the output at Y is equals to 0. These are the 4 conditions for the NOR gate. I think this concept is very clear to everyone. Now we will see the same point is explained here. All the four conditions are explained here in 2 points. Now we will move towards the NAND gate. Now the operation of this NAND gate is explained here. If both inputs are on, then only T1 and T2 are on and output is low. Otherwise, when either or both transistors are off, the output is high. This is the NAND operation on applied inputs. Now what it is saying, we will see one by one condition. If both the inputs are high, so first of all we will see the last condition. If both the inputs are high, means T1 and T2 both are high, so current will pass through the T3 and these both the transistors are in saturation region, so the current will come like this and go towards the ground. So the current is not passing through this direction, so the output will be 0. This is the last condition. And for rest of the conditions, if this input is if this input is 0, this is 1, then the current will come up to this, and if it is in cutoff region, so the current will pass through this direction and the output will be 1. Again, if this input B is 1 and this is 0, then this transistor is switched off, this is on. The current will come up to this, but if there is T1 is switched off, then the current will not pass in this direction, it will go towards the output and it will give 1. And the last condition is, if both the inputs are 0, it means both the transistors are in cutoff region, the current will come and go towards the output and it will give 1. So here we have seen all the four conditions for NAND gate. So this type of family is called as the MOS. Now cautions for using MOS devices. If any of input of MOS is left unconnected, the open input terminal, which has very high input impedance, may take any stray electric charge as input and can develop extreme dangerous high voltage which can damage the device and may also harm the person handling the device. Thus, none of the unused inputs of MOS device should be left unconnected. It must connect it to ground or supply. Even for storage of device, all pins must be shorted. So this point is very important. Otherwise, this device may harm the user. Now the CMOS logic family. CMOS stands for complementary metal oxide semiconductor, in which both P channel and N channel enhancement MOSFET devices are fabricated on same chip. This causes density to be reduced and complex fabrication process. However, CMOS devices consume negligible power and hence are preferred over the MOS devices in battery operated applications. So CMOS family is very important if we consider the power consumption. So we have seen in previous lecture that the fastest working family is ECL and the least power consumption is the CMOS. Now the CMOS is a complementary MOS in which both P channel and N channel enhancement MOSFET devices are fabricated. So this is very important difference between MOS and CMOS. Then CMOS is the family which uses P channel as well as N channel. So this is about CMOS. Now we will see the operation. CMOS family can be used for both NAND and NOR operation. Okay, so first diagram is of the CMOS which is designed for NAND gate. So here you can see the transistors. One by one you can see the conditions from the truth table and you can verify it from the circuit diagram. So in NAND operation, if both the inputs, that is if both A and B, both the inputs are 1, then the output will be 0. Okay, and for the rest of the conditions, if one input is high, one is low, then at that condition the output will be 1. So from the truth table you can verify the operation of the CMOS NAND gate. And similarly, in the NOR operation, if both the inputs, that is A and B, if both the inputs are 0, then and then only the output will be 1. And for the rest of the 3 conditions, the output will be 0. So this is the CMOS NOR operation. Okay, so from the circuit diagram you can see it is the CMOS family in which N channel as well as P channel both are fabricated on the same chip. So this is all about the CMOS. Now we will see the comparative study of these gates. As the mostly trending devices are the TTL, ECL and the CMOS. ECL is the fastest working family. It is the least power consumption is in CMOS. So comparatively, if we see TTL, ECL and CMOS, we will see first point, base gate. The base gate which is designed by using TTL is NAND gate. In ECL, if you see, we can design OR gate as well as NOR gate. If you see in CMOS, then you can design NAND and NOR gate. The fan in of TTL is 12 to 40. The ECL is having greater than 10. Fan in is greater than 10, and for CMOS the fan in is also greater than 10. The fan out for TTL, fan out means what? The number of gates which can be driven. So fan out for TTL is 10, for ECL it is 25, and for CMOS it is 50. The power dissipation in milliwatts, TTL it is in 10 milliwatt, for ECL it is 175 milliwatt, and for CMOS it is 0.001 milliwatt. So power dissipation is very less in CMOS, which is a very good characteristics, and thus the CMOS is the least power consumption device. Now the noise margin. Noise margin in TTL is 0.5 volt. In case of ECL, the noise margin is lowest, which is 0.16 volt, and the noise margin it is highest in CMOS, that is 1.5 volt. Now the next feature of the logic family is the propagation delay. In TTL it is 10 nanoseconds. In ECL it is less than 3, which is the lowest, and in CMOS it is 15, which is the highest. So propagation delay is lowest in ECL, and if you are having the lowest propagation delay, it means it is the fastest working logic family. The last point is noise immunity. It is very good in TTL. It is comparatively less in ECL. So we have written here good, and it is excellent in case of CMOS. So if you see from the table, the power dissipation is least in the CMOS, the propagation delay is lowest in ECL, and the noise immunity is excellent in CMOS. So this is all about the comparative study of all the logic families, and we have completed with all the logic families along with their circuit diagrams, truth table. So this is the end of logic families. We will see you in the next lecture with the new topic. So just revise all the logic families that we have studied. We have studied the first of all we have studied all the features that you can see here. Also we have seen fan in, fan out, power dissipation, noise margin, propagation delay, then noise immunity. Then in today's lecture we have studied TTL, ECL, MOS and the CMOS. And in previous lecture we have studied RTL, then we have seen DTL. Then in today's lecture we have seen TTL, then ECL and then CMOS. So all these points we have covered in today's lecture. So keep studying. See you in the next lecture. Thank you.